Hello, so this is a revision video for AP Chemistry 7.1, Introduction to Equilibrium. Some reactions in chemistry are reversible. Reactants react to form products, but then these products can react again to reform the reactants. Where a forward reaction is considered as reactants being converted into products, and the reverse reaction is considered as the products going back to form the reactants. A system is in dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic equilibrium can only be reached in a closed system, which is one where no matter can enter or leave. If a system is at dynamic equilibrium, the concentrations of all species remain constant over time, although it's important to point out that particles do continue to react. This is why it's referred to as dynamic equilibrium, because the reactions are still ongoing, particles are still reacting. It's just a system appears to us as unchanged because all the concentrations of species remain constant, hence equilibrium. Equilibria can involve either physical changes, like phase changes, or chemical reactions. In both cases, the forward and reverse processes occur at equal rates, but physical equilibria involve no change in chemical identity, whereas chemical equilibria involve the making and breaking of chemical bonds, forming new substances in each direction. For example, an open container of water will undergo both evaporation and condensation. Now, if the rate of evaporation equals the rate of condensation, then the system would be at equilibrium. This would be a physical equilibrium because no chemical change is taking place. The Haber process would be an example of chemical equilibrium. Nitrogen can react with hydrogen to form ammonia, and ammonia can then re-react to form nitrogen and hydrogen. If the rate of ammonia production is the same as the rate of nitrogen and hydrogen production, then the system would be at equilibrium. This would be an example of chemical equilibrium because new species are being formed in each direction. Graphs can be used to show how chemical systems change over time as it approaches equilibrium. Whether we're looking at concentration, rate of reaction, or partial pressures, the overall pattern is the same. There's an initial change, followed by a steady state with no change. For a concentration versus time graph, the concentration of reactants decreases while the concentration of products increases. Once equilibrium is reached, both levels flatten out. They remain constant. Though remember, the reactions are still happening in both directions. For a rate of reaction versus time graph, initially, the forward reaction is faster than the reverse reaction. Over time, the reverse reaction speeds up as more product gets formed. At equilibrium, both rates become equal, meaning no net change occurs. The system is dynamic because reactions are still occurring, but balanced, hence equilibrium. For gaseous reactions, partial pressure versus time graphs follow the same pattern as a concentration time graph. The graph shows reactants' partial pressure falling and products' partial pressures rising until both level out, the partial pressures remain constant, and equilibrium is reached. In these examples, we have assumed that we have started with reactants going to form products for a forward direction, but it's important to remember that equilibrium can be established from either direction. You could also start with products and they would react to form reactants and still form an equilibrium system.